will now make a presentation and greet us, because I'm also part of this group, and this really true connectivity across continents and across scientific disciplines.
Thank you, Anastassia. Good morning to everyone. Let me see if I can open here this greetings from.
Cumprimento a...
No, not this one. This is in Portuguese.
Cumprimento a todos os organizadores e organizadoras da conferência Abraçando a Complexidade da Natureza. Os temas que vocês estão abordando nessa conferência me lembraram o início da luta socioambiental lá em Chapuri, no estado do Acre, aqui no Brasil. Uma vez, numa reunião, o Chico Mendes falou que quando ele começou a luta em defesa das seringueiras, que era da onde ele tirava o sustento da sua família, achava que estava defendendo as árvores. Depois, ele descobriu que estava defendendo a floresta amazônica. Hoje, nós sabemos que ele estava defendendo toda a humanidade. E o papel dessa conferência de cientistas, pesquisadores, é exatamente esse: abraçar a complexidade das inúmeras informações que a natureza nos traz para poder realizar, a partir de diferentes saberes, aquilo que são os melhores caminhos para cada um de nós e para toda a humanidade. Podem ter certeza que eu aguardo com muita expectativa os resultados dessa conferência, porque cada vez mais é preciso fazer política pública com base em compromisso, bom senso e evidência. Tenham todos uma boa conferência.
Yes, this is. Whoever doesn't know, Marina Silva is a personality from Brazil. She's Minister of Environment for the second time now. And the first time she was Minister of Environment from 2003 and 2008. She was the only person who ever implemented a program that lowered deforestation up to 83% in 5 years. And now she's back, she's minister again since last year. In 1 year, she managed to lower deforestation 50%. So, and she, until 17 years old, she was in the forest. She was a rubber tapper. She went to the city, she got littered, and at age 32, she was a senator. So the youngest senator in Brazilian Congress. And she has a brilliant career. For those who know her, she's really fantastic. I'm so pleased she sent this message to this conference. And some of you know her personally, like Hilton, right? And so she's really, it was a distinction that we got her message. Now about going back to the risky business here. You know this, usually academic organizations, they tend to have inertia. And things that emerge, risky creativity that emerge outside the realm of the mainstream, they have a hard time in the beginning. You know, the startups in science, they're not well funded like startups in business, for example, or in technologies. So we put together this think tank, right? It's an independent, it's a small international gathering of scientists in diverse fields, transdisciplinary, and we have, you know, long careers, each one of us. We have more than 500 years of cumulative experience in this group, but it's a young group, it's a few years only, and we found the inspiration for putting this group together in the idea of the biotic pump. And biotic pump in the beginning was a controversial subject, and it's no longer. It's getting traction now in the mainstream. And but we cannot talk about this without making a simple introduction. And for doing that, I have a cartoon which I will play now. And
all around the world, traditional wisdom has it that forests bring the rain. Scientists have scoffed at this notion for a while. Forests grow where there's ample precipitation, but they do not cause that precipitation. It comes because of winds that are governed by geomechanical processes which have nothing to do with where the forests are and aren't. Water does not tend to stay in one spot for very long. Most of it ends up running off into the ocean via rivers. Unless there's some way for the moisture from the ocean to come back inland, all of the land's water would be gone very quickly, as with the forest. According to the geomechanical view, moisture gets transferred inland when water vapor is carried from the ocean by winds. Because some of this water gets lost to precipitation, the deeper inland this air gets, the less moist it becomes. Therefore, deeper inland means less rainfall. If this view is true, we should expect to only see forests near the coasts, and drier, more arid areas the farther inland we go. But this is not what we find. Where there are still natural forests, precipitation does not decrease with distance from the ocean. In fact, it often increases, the greatest amount of rainfall being in the deepest parts of the forest, sometimes thousands of miles from the coast. This is unexpected and difficult to explain with the geomechanical view. What on earth could be attracting so much water to a spot so far from the ocean? And why? While there is more water in the ocean than in forests, forested areas have more water vapor in the air. This is because forests, especially healthy ones, have a lot more surface area for water to evaporate off of. Multiple canopy layers, shrubs, moisture-laden ground are all full of water which transpires or evaporates entering the air. As a result, we find much more water vapor in the forest even when there is less total water. The ample amount of water vapor in the forest rises and condenses into clouds, changing from gas to liquid. This creates a drop in air pressure, which allows even more vapor-filled air to rise. This creates an upward air current, which in turn creates a horizontal current closer to the ground. This sucks in air from higher pressure areas, like the air from over the ocean. This air contains some water vapor, which increases the total amount of water in the forest, leading to more frequent rainfall. Essentially, forests create a giant constant air current that attracts moisture from hundreds of miles away. This is how we find so much water so far from the ocean. The forests bring it in. This process is known as the biotic pump, and it shows how traditional wisdom was right all along. Forests really do bring the rain. So as more forests are clear-cut, the more extreme become the droughts, and the more expansive become the deserts. If we want to thrive on this planet, we need to preserve and regenerate the forests.
We are a little bit behind schedule, so we pass to the next session, right?
And I would like to introduce our moderator for this session, where we will discuss basically the conceptual why we need this conference at all. Why do we need new approaches to how we view the importance of nature and the importance of water? And our moderator will be Professor Susan Masino from Trinity College, and she will lead the session.
Well, I would just like to first open the floor to Professor Jan Pokorny from Enki and let him take it away so we can keep on time. Thank you.
Thank you for the invitation. It's really a privilege. I have 10 minutes, too many slides. They're afraid. So, we did research in school. 600 students, 100 teachers of biology, and we asked, how can plants influence our atmosphere through responsible O2 production, but almost nothing about water? And then we asked, what part of solar energy is fixed in the biomass, plant biomass? Correct answer was from 8% of people, because plants just take into biomass about 1% of the solar radiation. Okay, then we asked what the plants do with the water. What is the fate of water? And imagine, and the same is in Europe, in other countries. No water is, all water is used, water is not released in the atmosphere, and almost nothing known about the cooling effect of the water evaporation. Okay, thank you. There is a project, Erasmus, 6 countries, including Germany, education for plant biology, how to put into our knowledge on the level of education the basic facts and basic information. The books will be this year. So sun heats us of 290 centigrades, and what we do with the solar energy. Without sun, it would be solid atmosphere. So let us think what we do with the solar energy, which is light. It's this from the sun, which has 6,000 degrees, and we have 300, and we emit the long wave radiation. We can measure it, we can measure evapotranspiration. There is a short wave radiation, which is the yellow one, up to 1,000 watts. Then there is a reflection, there is a heat flux to the atmosphere, and then rest is so-called net radiation, and we people decide whether it will go to water vapor or whether the substrate will be hot, 50, 60 degrees, and then hot air up. Let us compare 2 longest days in our region. This axis is a watt per square meter and daytime. There is a clear sky, and we have up to 900 watt per square meter, which is the red line. Then we have reflection, it's a blue line, and we have the flux of the long wave radiation, which means heat, in the atmosphere. There is a sunny day, 900. There is a cloudy day, it's 10 times less, and then the temperature of the sky is under 0, and we have over 20, over 30 degrees grass and so on. When there is less solar radiation, the temperatures are very similar. So we have to think, if we have clouds, we have less solar radiation. If we don't have clouds, we have more solar radiation. The question is, how do we affect clouds? There are works showing that there is an increasing impact of solar radiation in time, which is caused by less clouds. There are people saying it's less of aerosols, better air, but we forget on the effect of vegetation. We forget on the evaporation, as was here several times mentioned. Because when we measure long wave radiation, it's increasing. The flux from the surface of our landscape, the atmosphere, is growing. There are techniques which are very easy and very demonstrative. We are on the Rathaus in town hall in my town. We are looking at the roofs, and they have 50 degrees. We are looking at the meadows, and they have 25 degrees. And so not color, but evaporation, water is important for the temperatures. This looks very scientifically. Important is average value of evaporation is 240 watt per square meter, because it's a good number. It's 100 milligrams per second per square meter. Let us have a look closer. We have 1 liter of water. This 1 liter of water, to be evaporated, needs latent heat, which is 0.7 kilowatt hours. And from 1 liter of water, we have 1,200 water vapor. Let's go at the tree. There is a pavement and full sunshine. 877 watt per square meter, 51 degrees. Let's go under the tree. There is 80 watts per square meter and 27 degrees. Because there is a flux of water through the tree, and 20 liters per hour, 20 times 0.7, we have 14 kilowatt cooling effect of the tree. We cut tree and we put here air condition. What is the difference? Air condition heats us, and the tree sends solar energy to the places where the water vapor condenses. The dry places look innocent. They don't evaporate water. Could be any damage. However, dry place is hot. Hot air goes up and sucks the humidity from the pond, from the forest, and we say don't make ponds because they lose water. Let's go into the forest. Forest has inversion temperature. Lower down, higher, relatively higher here. And lower temperature means heavier. When we compare forest with the, let's say, maize, then the temperature in the crop is a higher low, so we have again this flux of air up. You will see in excursion that sometimes no touch, no action is not good. We have a lot of bar beetle and dying forest, and there is a lot of temperature 50 degrees. We need living forest, different structure, and we know what species are necessary for it. And so here is temperature about 25 degrees. Bill Nage, chief editor of ecological engineering, author of the book on wetlands, asked me, have a look, what do we make with the solar energy when we dewater in United States 400,000 square kilometers? And I told him, multiply it by 240 watts per square meter, and it's a huge change of the solar energy distribution we cause. We are in South Italy now, and South Italy has a problem with the water, no rain. So what we make the greenhouses, but greenhouse means again less and less evaporation. And this is what we saw on the movie. The clouds are on the coast, and they don't go inside because there is a hot air. So climate change is more serious than global average temperature shows. Dry cities, landscape overheat, ancient civilization dried out, and we don't have in environmental impact assessment this shift from evaporation to heat footprint. So there is a fundamental contradiction. Evaporation must be limited because it's waste of water, or evaporation is really the basic process which makes planet living. Jan Čermák, he measured a lot, and here are the last pictures. 1 square meter of root zone, several meters of skeletal, 1 kilometer fine absorbent, and thousands of kilometers of mycorrhizas. And it's easy to do these things. You can take this thermometer, which costs $50, and you measure the temperature here and here. So if here is -20 in sky and +14, I look, these are last pictures. On Nick, we were together, Nick Pacini in Naivasha, so sand has 60 degrees. Succulent has 40 degrees. And we go here in the forest on the shore, it's 20 degrees. Then people come and cut the Mau forest, 1,000 square kilometers. You have a look on it from the satellite and you see that where it was cut is the temperature 30, 40 degrees, and you can evaluate. Let's go inside the forest. What was cut, and it's green still, there is a 40, 50 degrees. And then we go 50 meters into the forest, and person is the warmest one. I am from the countries or regions 300 kilometers from here. There are fish ponds, a lot of fish ponds. I think it's one of the way how to manage landscape. Homer is the last one. It's for wine. So we heard that the trees are cut in order to put the photovoltaic or the wind. How much oxygen was released in? We have one tree, 1 cubic meter. How much oxygen was released during life of this tree? how much carbon dioxide taken, and how much water was evaporated, and how much energy, soil energy, was converted into the cooling and climatization effect. It's all.
Thank you so much. That was phenomenal.
Did I manage?
Yes, you managed very well. Yes, thank you for handling the computer. That was an incredible overview of the really powerful effect of local decisions on all of these processes. The next speaker will be Andrei Nefiodov. He's a collaborator here at TUM, also a member of the Biotic Pump Greening Group, and faculty at the Petersburg Nuclear Physics Institute. So this is going to be a more kind of global message from Andrei. Please.
Thank you. How to approach the problem of climate change? In order to solve problem, one needs to formulate it in the correct way. And for this purpose, you need to choose the correct concept which is consistent with the well of experimental data. At the moment, we have two alternative approaches. The first one, conventional one, considers the environment suitable for life because of unique conditions of the Earth's surface. Is just lucky chance of the because of lucky position of the Earth on the circumsolar orbit. The second approach, which is called biotic regulation concept, and it was developed, founded in pioneering works by Viktor Gorshkov, Russian physicist. The view on environment is different, and according to this second approach, life itself, or biota, which consists of flora and fauna, creates and maintains an optimal environment for itself. In first approach, life adapts to any environmental changes. In second approach, life compensates for any unfavorable environmental deviations from the optimal. In first approach, there is no difference between natural and disturbed ecosystems. In second approach, natural ecosystem has a fundamental meaning because it's function in such a way that it stabilizes the environment. But disturbed ecosystem destabilize. What is the difference between natural and disturbed ecosystems? Ecosystems, first of all, include some community of species. It is generalization of living organism, which has some internal structure. It has some parts, correlated parts, and these communities interact also with substances of environment and other systems. So the main difference between natural and disturbed ecosystem is that natural ecosystem is self-sustainable. It is able to recover itself. When the forest on land is damaged because of different perturbations like bug beetles, fires, and other stuff, windfall, it comes through different stages of succession, and it takes hundreds of years to restore itself, and it can do it by itself. If the system is disturbed, it can be trapped in the early successional state, and it cannot go further, it cannot proceed. So there is a steady state which is formed by human species, and in this state forest has no aging. It can exist forever. This is the main difference between natural and disturbed ecosystems. Natural ecosystems can create and maintain environment. So we call them climate regulating forests. To get you some ideas about important quantities and numerical figures, I'll show you some example. Imagine that everybody sitting in the room is billionaire. 1 billion euro is 1,000 millions. It seems to be a big number, but another quantity which characterizes the money is not the money stock, but rate of consumption. Imagine that you have rate of consumption, outflow, 100 millions per minute. And it means that you can consume all the amount of money that you have within 10 minutes. Okay? And now the question is, imagine if you want to have the money amount, billion euro, stable enough for longer time, for, let's say, for lifetime of human beings, for 100 years. How one can have the same amount within so long time? You need to compensate a rate of consumption with a rate of production. So you need to have inflow and outflow correlated. And it means that in this case, you need to have inflow and outflow under control. No other way. And these numbers actually are very close to what we have in reality in nature. There are lots of measurements about carbon. Carbon is a basic element which consists about 10% of living mass, and it is known the stock of organic carbon in atmosphere is about 1,000 gigaton. Flow of carbon, which is known as also as a net productivity. It's a rate of organic production without respiration, is 100 gigaton carbon per year. And it means that if we have only production of organic, then the turnover time is just 10 years. But we know that life exists for billion years, and for ecosystem lifetime, it's about dozens of million years. How one can manage to keep an environment in a stable state if it can destroy it completely within 10 years? It can only be possible if synthesis and decomposition of organics are correlated. They used to balance the environment. And there is no other way. The earth must be under control. To make the further feeling about the numbers, the excess of atmospheric carbon in atmosphere, which is accumulating, is 5 gigaton carbon per year. And you need to compare with net productivity of the biota, which is split 50-50 between ocean and land, 100 gigaton per year. So forest is 10 times more powerful than the excess of carbon to the atmosphere. And I would also want to mention that the turnover time for water is the same as for carbon, 10 years. So if we take into account only the outflow due to the river flow to the ocean, all the water on land can go to the ocean within 10 years. So sustainability of rivers can only exist if there is an inflow of water in form of vapor through the atmosphere to the land from ocean. Another point, so we mentioned about, we was talking about energetic power of nature, which is measured in gigaton carbon per year. And one can relate mass and energy, and in fact it is an energetic power. I would like to also to mention you the informational power of biota, which is actually as a network, is working as a network of microscopic computers. Even some living cell, like plankton, plants, bacteria, fungi, are functioning as a laptop. And in addition to energy power, it has also information capacity. It has, like computer, it has hard disk with information, and it possesses also the information power, which describes the information processing rate. And it's measured in units of information per unit of time, bit per second. We have heard already that sun radiates photons which are 20 times more energetic than thermal photons, because the temperature of the sun is 6,000 Kelvin and average temperature on Earth is 300 Kelvin. And because of this difference in energy, solar photons can excite molecular cells in any living cell, memory cells, and can prepare the excited cellular molecules. And in fact, each process of excitation on the molecular level is a transfer and information, each of 1 bit of information. And knowing the flow of of solar photons, one can estimate the informational power of biota. It's about 10 to 35 bit per second. And this number is 20 orders of magnitude larger than we have in human society. So, in energy power of biota is about 10 times more larger than we have in society, human society, but informational power, 20 orders of magnitude. So this power, this cannot be, it will never be, we will never be able to reach even this value. And concluding, I want to say that solution of the problem of climate change can only be found within a framework of biotic regulation concept. Natural ecosystems are unique with respect to the energy and information flows and cannot be substituted by artificial tools. Living organisms composing the natural ecosystems are genetically coded to maintain the environment in an optimal steady state, and loss of natural ecosystems is incompatible with environmental sustainability. The more extensive natural ecosystem we have, the more significant their stabilizing impact on climate. Some original publication on the topic you can find on our website. Thank you.
Andrei, that was phenomenal to think about what are the right questions to ask and what's the scale and mathematical possibilities in the system that we're trying to understand. Our next speaker this morning needs really no introduction because we're all here because of her visionary work and inviting us here. Dr. Anastassia Makarieva. Please.
So how can we integrate what we have said so far, the importance of nature, the importance of water, and the importance of complexity into the narratives that we are having now? So what is the familiar narrative concerning global change and our existential problems? You see, you can already anticipate what I will be talking about, right? So CO2 accumulation warms the planet, okay. To save the planet, we must decarbonize. So this seems like a complete solution, but did we forget something with this narrative? Yeah, something small. Something that doesn't actually fit. But we also appreciate biodiversity when it doesn't stand in the way of decarbonization, right? So we like these things, but we prefer solar power and like biofuel. So we sacrifice sometimes. And what are we proposing here and offering for your judgment is a different narrative. It is not like totally like we'll solve all our problems, but it is a different perspective. So CO2 accumulation warms the planet, okay. But the more so, the more we exploit natural ecosystems. So to save the planet, we must protect natural ecosystems, thus decreasing climate sensitivity to CO2 accumulation. And may I ask you, do you know what climate sensitivity is? Just could you raise your hand who knows? Okay, one. by how much our planet warms when we add a given amount of carbon. Like we double carbon dioxide and we have a temperature increase. But it can, for a big CO2 change, we can have smaller temperature change, or we can have a very big temperature change. And this is climate sensitivity. And this sensitivity is very poorly known. Because temperature changes are irregular and observations are not perfect. So basically, modern climate models give different estimates of climate sensitivity that range by several times, like from about 2 kelvins per CO2 doubling to almost 6 kelvins. So this is a very strong effect and a very strong uncertainty. And so how can we visualize it in terms of storytelling? So imagine this sensitivity. Imagine this man is CO2. This is the Earth. This is the warming. So CO2 is pushing the Earth towards warming. And our familiar narrative is the more CO2, the more warming we will have. Okay? So now let's embrace nature complexity. We can have this situation with low sensitivity, which means that it is very difficult for this guy to push the planet in this direction towards warming. Because there is a certain buffer out there that doesn't make it easy for him, okay? And this is high sensitivity, right? So even one guy could push the planet far, far towards the dangerous warming. Because this is high sensitivity to CO2. So we have less natural biota, more warming, even with the same CO2. This doesn't mean that accumulating CO2 is unimportant. It just means that changing from this to this, we are really undermining our existence. So our existential problems, if we make a like bigger picture, is that these natural ecosystems what keeps the Earth stable, not letting this guy push it to unfavorable states. Okay. So the next question is, how does, if we think of it, how does the biota do it? Do we know anything? So should we like consider it a fairy tale that somebody thinks, oh, some biota, what is it at all about the biota? But do we have evidence showing that natural ecosystems do have in fact the capacity to make this cozy pit or within the interval of life compatible temperatures? And yes, we do know that natural ecosystems are very powerful regulators of clouds. And clouds are the most complicated element of the climate system, because clouds can both warm and cool. And why they cool? Because they reflect sunlight, so less energy is coming, so it is like understandable. And but they can also warm because clouds like CO2 interact with thermal radiation from their surface and partially redirected back to the surface, so they are part of the greenhouse effect. And so by carefully playing with clouds, the biota can regulate temperature, and this could be, and we do know, and there is extensive research mapping this, that trees emit, and forests, not even trees, but the whole community of species including fungi and bacteria, emit certain particles that facilitate cloud formation. So this is just one example, because it's such a complicated and extensive topic, but just to give you some idea that this left graph shows the frequency of shallow convective clouds, so those clouds that cool over different land cover types. And we can see that they most often happen over forests. And this is across all regions of the world. So this very interesting study shows that basically forests in the Amazon and in Eurasia and in North America are similar, that they, when it is warm, they produce these white shields and basically keep the environment habitable. And what this second graph shows, that not everything green does the right thing. And this refers to what Jan and Andrei were talking about, that there is information processing capacity associated with different ecosystems. And here you can see the blue symbols are how the forest, the cloud cover, percentage of cloud cover grows with a measure of leaf area index. So the more green life in the forest, the more cloud cover. And these purple symbols is non-forest. So these are at high values of enhanced vegetation index. We have highly productive agricultural systems, for example, but they don't produce clouds. So when we replace natural forests with something of our immediate needs that provides for, which is also important, but we need to understand that we change this genetic program that regulates ecosystem interactions with the environment. And so, sitting here in the 21st century, it is really like hilarious that we still have a tendency to view life simply as a physical-chemical system, while we know that information governs everything. We have come to the appreciation of artificial intelligence, of these supercomputers, but we have this ultra supercomputer in our, like, in front of us, and we think that this is just a simple chemical reaction, CO2 plus just simple production of carbohydrates. This is not so. It is a very dangerous, it is actually an atavism, this view of life as a simple physical-chemical system. It is how it is introduced into the climate models in terms of simplified parameterizations. This is an atavism of our under-appreciation of complexity of the world. So we should grow up to appreciate it. And so this boring graph, but it, and very like, not very like engaging, but it actually summarizes the drama of what's going on with the planet. Because in recent century, we've been losing primary ecosystem, both forests and non-forests. And at the same time, we were polluting the atmosphere with CO2. So, this combination, these two green curves is actually, we have been undermining the systems that could help us cope with our problems. So, to to fight climate destabilization, we need to cooperate globally and to stop this destruction of these systems, because we still have a lot of them. They are still there, and if we just stop their destruction now, as Marina Silva was alluding to, we will prevent the situation from getting worse. We are not yet at the bottom. A long way to go. So if we just stop now, we will be doing almost fine. And this will buy us time to do other things and to cope with other problems. Thank you. We will now have a discussion and with questions, and we have yes. This is part of the webinar. Okay.
Yeah, sorry, little glitch. First we have a few slides from Antonio Nobre's. He wants to lower the blinds. We're in trouble for lowering the blinds because it's noisy and we have a sound problem. So we'll see what happens if he goes rogue on that.
Yeah, nothing against the light, but I love contrast. When you have light coming from the back, the contrast gets washed away. So some of, I don't know what you prefer, but if you could allow us to.
It's just the sound.
Yeah,
I think
okay,
if you
this
actually,
one,
like,
but for the
function.
next presentation, please, we can go. I would really, this fostering some risky creativity, talking about subject. Okay, now, I was touched by Andrei's mention and then Anastassia reinforcing of the microscopic complexity. So Anastassia asked me to bring a little, very quick thinking, like exercise, about this topic. And this topic especially relevant for us today. And the reason is, we don't know, talking about Socrates, we only know that we don't know. However much we know, it's not enough to describe the complexity of the natural world. So we have sciences thriving on unknowns, right? Science is the subject where we seek for new things all the time. And the problem we have today is that because we know so much, we are sort of lured into believing we know enough. And we don't know enough, and I will try to bring here a reflection on this precisely, this notion, using a little bit of art. We live in a matrix. You know this, Keanu Reeves from the Matrix series, he said that the Matrix is a documentary, not a fiction. And the Matrix is about dystopia. But we have another matrix. I call it utopian matrix, which is nature. And we are not aware about this matrix precisely for two reasons. The first one is miniaturization. We, in the Western world, what is the saying? What the eyes don't see. What is the saying in English? The heart doesn't feel, or?
Something like that.
Yeah. So if you don't see it, you don't care for it. Not for indigenous knowledge. We will see this later. But to illustrate this very concept that we ignore what we don't see, I brought here some few numbers. You will think this is far-fetched. You think this is not wrong, but it's not. I double-checked this and I found another reaffirmation of this. You know, DNA is this simple molecule that has 2 nanometers across. In each human cell, it can stretch, if you unwild it, to 2 meters. So in a human body, we have 37 trillion cells. If you multiply this 2 meters by that number, you have that in a single human, you can have 178 billion kilometers of DNA. You can go back and forth to the sun 600 times with the DNA each one of us having our own bodies. Can you imagine this? Now let's put together the humanity, 8 billion people. You can go 30 times back and forth to Andromeda galaxy, which lays 2.5 or 3.5 million light years away from the Milky Way. If you can collect the DNA from all the biosphere, including microbes, including what Andrei was referring as microcomputers, then you have enough length of DNA to cross the known universe, 93 billion light years, a few times. This is all contained within ourselves. This is information, the most fundamental information, genetic information. And this is all hidden from view. So this is basically what I'm saying about the matrix. We ignore it. And in native knowledge, I heard indigenous wise people saying that we have the universe inside. And that's the size of the universe, okay? The second reason why we ignore what is below our level of microscopic life is automation. You know, back in the early days of the cars, where it smelled gasoline, it was noisy, etc., you knew what the machine was doing, because the engine was cranking. In the early days, you had to crank it to start, etc. These days, you get in a car, even a combustion engine car, and you turn the key and you don't know what is happening under the hood. Why? Because automation. And to illustrate this automation, I made some calculations and I found some references as well. In a single second, in each one of our bodies, we have from 1 quintillion to 1 sextillion chemical reactions mediated by enzymes. It's happening right now. Everyone here in this room is having this rate of chemical reactions to keep us alive. This is a number so huge. You know, 1 quintillion is 1 billion trillion reactions. It's happening completely silently, and it's happening inside us. So the connection I want to make here is with artificial intelligence and neural networks. You know, the more we develop the field of artificial intelligence, the more we understand, or the less we understand what is happening inside the neural network. We don't know what's happening there. It's too complex. And nonetheless, we are seeing the evolution of artificial intelligence before our eyes. Fantastic in the last year. And promising wonders. And we don't know what's happening in the heart of the system, in the neural network. And it's basically exactly what life does since billions of years. Neural network. This information, this universe of information, is what gives life the competence that Andrei and Anastassia mentioned, that you saw also as a reflex from Jan Pokorny's presentation on temperature. And this is the backdrop I would love that you keep in your mind about the whole story we will discuss in this conference. Okay, that this is about embracing complexity. It means when you embrace someone, when you give a hug, our hearts get close together, and I call this the love Wi-Fi. Is when you communicate. That's how we have to embrace nature, because our hearts know about it. Our hearts connect every cell in our body. We need connection. That's why the heart is the best organ we can, enlist for this task. Is a huge task. We cannot overcome this task without love. So, and then I close with this animation made by Andy Lomas. and he's incredibly creative. He made a computer model of cell multiplications, mitosis, right? And he changed the algorithm, and then you have different tissues evolving from a single cell. And I don't know if who are here from biology or related field? Okay, medicine, biology. Okay, so this is a phenomena that's going on all the time, because if you don't have cell replication, you don't have the renewal of tissues, you don't have the formation of bodies, etc. And even a single leaf or a flower or a tree growing is undergoing this continuously. Imagine, in our body we have 37 trillion cells who are doing this right now. And we have not a complete explanation how it comes. Because differentiation means you have different cells, but they have the same genome in a single body. And who is coordinating this symphony? It's a choreography, you see. There is a program controlling it, and we have very little information. We know the hardware, we know the molecular biology side of it. But I still am waiting to see the software that is commanding this multicellular symphony, and dance is a choreography. And depending on how it goes, you have formation of different cells. This is so, I call it, I love the elephants, you know. Elephants are wonderful creatures. But when you have elephants in the room, it's usually a very tough situation, because you want to take the elephant out, because otherwise, especially in a crystal shop, you say you have an elephant in a crystal shop, we have too many elephants in the room. This is an elephant in the room of biology. We don't explain morphogenesis the way we should. And this is another dimension of complexity, of life complexity, that we barely touch on it. We know the functioning of molecules of DNA. The proteome is a follow-up of the genome project. It's finding that inside cells you can have, I don't know, 92,000 proteins, each one commanding those quintillions of reactions happening inside our body. So everything works. It has gone on R&D, research and development, for billions of years. So we should pay respect and reverence to this complexity. Okay, thank you.
Now I'd like to invite all of the speakers up for a panel, and also invite Eric DeGuys, science journalist and author of Water Always Wins, and Professor Hugo Bardi from University of Florence. Please come up.